So how's it so far? Okay, great. So we get all the way down to here. And last but not least, in particular, show that the number of steps is at most 7 times the number of these digits. So we know that given that the Euclidean algorithm terminates in at most, well, we don't have to write as 2n anymore because we already know the results of 2n. So we're going to use the results, okay? Steps such number, then we're going to do our calculation here. Begin algorithm. So we have this here. It's going to be equal to 2. So log again, we're going to use the identity. So we can rewrite log base 2 into fraction ln of b over ln of 2. Or actually, we can, again, it is not forced to be using natural log. We can actually use any base. So we can actually do something like this. We can change it base 10. Like so. But more than that, we actually also know that when we write the fraction, that part there, we can actually flip it. Again, that is that is like saying that. How should I answer it? Well, we don't have to write like just write log instead of log base 10. We all know what log is. We have something like this. Okay, maybe I should write it as multiplication. Okay, then this is same as 2 dots log b times log 2. We can write 1 over log 2. We can rewrite again. We can use the we can write as log ln 2 over ln n over n, and then we flip it. We can rewrite as ln over ln 10 over ln 2, which is same as log base 2 10, like this. Then this is same as 2 ln base 2 of 10 c dot ln log b, where now we need to find out this number here. So we're gonna use a calculator quickly to calculate it. Okay, calculator. So we have what we're trying to find. ln 10 2. Okay, so which is same as again this is ln uh s- maybe I should do it this way. What is log 2? Log 2 is this, and then we're gonna take the reciprocal of it, answer. So we get something like this, okay, times 2, which is what we have. So we see that this is approximately equal to what is given, 6.644. Let's go for a few more digits. 6.644. Okay. Uh, so back to here, 6.644, which is strictly less than 7. Okay. So our answer is thus the number of steps is at most 7 times the number of digits in B. So again, this coefficient here is telling us how, remember, we call it, this is telling us how many steps we're gonna take, right? So since log B here, or log base 10 of B, is actually telling us the digits of B minus 1, of course, in this case, then we can multiply by well, actually it's actually telling us the number of digits, in fact. And if we're multiplying by the constant here, which is telling us how many times approximately the number of steps is. And this coefficient here is telling us the ratio between the number of steps to the number of digits in B. Okay, therefore we can see that this is a linear is kind of like a linear relation there. Okay, or direct is a direct relation. So this is strictly less than, well, this coefficient is strictly less than 7. So approximately, we can see that it takes about it can when I say at most 7 times, meaning that it cannot exceed 7 times here, and this is based on the approximation that this linear equation is going to be well, we can write as less than 7 times log base 10 of B. Okay, and see that the slope, or the coefficient here, which is playing the role of slope, is actually telling us how many times this ratio is going to be, which is no bigger than 7 times. So at most 7 times. Okay, and therefore we actually have finally complete problem 3, which is actually quite a long problem, surprisingly. Whew. So now we actually have 3 problems left, problems 4, 5, and 6. So I actually need a 5-minute break, 3-minute break, and we're gonna come back very soon to continue working on problem 4 here. Okay. Okay, so let's continue. Um, Number 4. A number L is called a common multiple of m and n if both m and n divide L. The smallest such L is called the least common multiple of m and is denoted by LCM of m and n. For example, the LCM of 3 and 7 is 21, and the LCM of 12 and 66 is 132. Okay? So, part A, find the following least common multiple. So, in fact, there is a trick. Um, well, the trick is actually in part B, so I'm not supposed to spoil it out. So let's try to do it. And besides, these numbers are actually not too big. Okay, so to find the least common multiples, we actually need to uh, do it in the following way. So begin the solution. So what we need is first we need to find out the GCD. So notice that the GCD of, well, 8 and 12 is actually quite easy. We can see clearly it's equal to 4. Implies that the LCM, well, actually write in lowercase, but it will power in uppercase. So great. LCM of 8 and 12, well, we actually know that it's 24. But how do we actually do it? Well, in fact, we can actually write in the following way. GCD is equal to this 4, which is equal to 2 squared times 2 squared. Okay. So what we actually need to do is LCM of, we're gonna rewrite those numbers into unique prime factorization, meaning that, for example, 8 is going to be equal to 2 times 2 times 2, or 2 to the third power, and then we're going to rewrite 12 as 2 squared times 3. So that now when we want to take the least common multiples, what we actually need is we just need to collect the highest power of each factor. So each prime factor. For example, we see a prime factor 2 between the two numbers, and then the highest power of 2 we see is a 3, is a third power. So we see that in order to be a common multiple, we have to take 2 to the third power uh, as part of the factor. Otherwise, if we have less than 3 copies, it won't be able to be a multiple of 2 to the third power, which is 8. Similarly, we have 1 copy of 3, or 3 to the first power, and we just need to take the minimum. We need to take the maximum. We need to take the minimum amount of the maximum exponents. Okay, maximum copies. So the first number has no copy of 3. The second number has 1 copy of 3. So we just need to take 1 copy, and it will be good enough. And therefore, we actually get the results 2 to the third power, which is 8 times 3 is 24, as our final answer. Then next we have, and for everyone who actually missed it, you can always watch, go back and watch it again, and then hopefully you guys will be able to learn something. Anyway, we're gonna continue working on this problem. GCD of, we need this. GCD of this is clearly 10, which is 2 times 5, implying that the LCM of 20 and 30, which is again equal to the LCM of 2 squared times 5, and then 2 times 3 times 5, is going to be equal to, we see at least 2 copies of, we actually see 2 copies of 2, and then we see one copy of 3, and then one copy of 5. And again, that and 2 squared is 4 times 3 is 12 times 5 is going to be 60. And if we pay attention carefully, we actually don't even need to think of what the GCD is, and then we'll be able to find out the result. So in fact, we don't really, we can actually delete this. We can delete this for now because we can explicitly find out the value. Of course, later on when we answer the problem in part B, we actually need to find out the GCD. Well, somehow actually need to use the GCD to actually get a relation. Okay, so next we have 51 and 68. So let's see. The LCM of 51 and 68 is going to be equal to the LCM of what is 51? That's 3 times 17. And then the next one is 4 times 17, or 2 squared times 17. To give us minimum, we need 2 copies of 2, 1 copy of 3, and 1 copy of 17. And then again, 3 times 17 is 51 times 4. That's going to give us 204. And we actually found the answer quickly. Last but not least, we have the LCM of 28 and 18. Well, clearly 28 is already a prime, and 18 is actually something smaller than 23 and cannot be a result of it. So we can in fact try to rewrite. We don't have to rewrite it in this case, but if we rewrite, we'll still be able to kind of see why. Okay, so if we rewrite it, we actually need to take everything in minimum. Then we have 2 times 3 squared times 23. But that's again same as the first part is just 18 times 23. That is going to give us, let's see, uh 18 times 23. That's giving us a 414. Okay, so we actually found our answer for all 4 parts. Wonderful. And of course, we have the last one here. Okay, then part B, we need to find we need to compare the value of this to the value of mn and gc of this. Okay, then try to find try a value or try a relationship. Well, this is in fact something that I've done in one of my old videos. We actually show that um, the LCM of M and M and N and GCD and the GCD of M and N is actually having a relation that's the product of LCM and GCD is equal to M times N itself. Okay, so I'll quickly answer this. So here is a solution. LCM of M and N times the GCD of M and N is equal to Mn. Okay. So, well, this is not supposed to be part of the answer, of course, but for now, this is you guys can actually see why. One of my old videos for explanation or for the proof. Okay, and I'm not going to spend my time to go over that proof again. Okay, so quick idea: we can write m and n uh, as well. We can let GCD of m and n be g, and then we can see that the LCM will be equal to uh, g times m over g times n over g, because again, we in order to go through a detail, we need to rewrite m, n, and g in terms of all the all the prime factors: p1, p1, p2, p3, so on and so forth, q1, q2, q3, so on and so forth, and then say that G is some of the ones that is being repeated, and then you can raise it to somehow or some different powers, and then we will need to do all kinds of collections and stuff like that in order to get the results we need. Okay, anyway, good. So let's move on to the next problem. Okay, next part. Give an argument proving that the relationship we found is correct for all m and n. Okay, again, I'm not going to answer. I'm not going to answer this again. Just watch my video, and you guys will be able to see why. Then next, use your results in B to compute this LCM. Okay, so now we are trying to find the we want to find the GCD in order to compute this result, because the thing is that we in the first problem we have actually learned a different method to find GCD. So if we try to use the method we have done in part A in this problem, we see that what we are doing is we're trying to break the numbers into prime factorization, and then try to pull out the prime factors with enough power or enough degree in order to get the results. But on the other hand, we can also use we can also use the Euclidean algorithm to find out the GCD, the greatest common divisor, instead of trying to list out the prime factorization and try to find out the minimum amount or the maximum amount we can have, based on the minimum degree we have that we actually obtain. Okay, so we're now going to use this new result from part B, which is LCM times GCD is equal to the product of the two original numbers, and we're gonna use it we're gonna use the Euclidean algorithm to find out what the GCD is, so that now we can actually find out the LCM with the given m, given n, and the given the GCD that we found. Okay, here we go. So solution. Let's see. So by Euclidean algorithm, so we will try not to get all the result in one single step, but we're gonna practice a little bit more of the Euclidean algorithm to find out the GCD. So we have the two numbers 301,337, 307,829. So clearly we have the second number is bigger. We are gonna start with that 29, and then we're gonna divide by the first number 337. And again, we only care about our remainder. So we will go back to root rem alpha, and then we're gonna do remainder of this. So right now here, so we see that the remainder is, well, this time they actually somehow box it in the front. It's gonna be 6492. So going back, I'm gonna type it down 6492. Then since it's non-zero, we're gonna take the step again divided by the new remainder 6492. Then this is going to give us, let's see, 6492. So this is what we have here. So this time we have 2705. So back to here, 2705. And since it's non-zero, we'll repeat that one more time. And again, our goal is to find out the steps that we need in order to get down to 0. So back here, we're going to divide this one by the new remainder 2705. This is going to give us something a lot smaller, 1082. Here 1082, and again non-zero, so we need to continue. So 1082, and again back to here. If we keep going, we actually can. If we're getting used to the step, we can just keep doing it. We don't have to write. We don't have to write all this, like all the intermediate steps, because our goal is to find out the 0. But here we're gonna show in this problem, because we're not familiar of it yet. We have 541 non-zero. We're gonna do it again. So 1082 divided by 541. In fact, we don't have to use it, because we see that if we multiply 541 by 2, we actually get to what we have. We get the dividend, so we actually get a 0 here. Okay. We get the GCD of these two numbers. First number is the smaller one, and then the second number is the bigger one. This here is going to be equal to 541. So this is the GCD here. Thus, the LCM of these two numbers is going to be equal to the product of these two numbers, 337 times 307, 829, and then divide by our GCD. And this is going to be equal to, again, we need to use the calculator again. So we have, let's see, we have 01337, 301,337 times 307,829, okay, times 307,829, and then after that we're going to divide by 541. So let's see what we get. We actually get this number here. So this is going to be our result. And see, we should expect to get an integer back. If we don't get an integer back, then clearly we're dividing by the denominator here is actually not a GCD, or not even a factor, because we should expect that this LCM is a multiple of the integers, so it should end up with an integer. Okay, so that's a quick way of checking our answers or not, but not it's just a rough way to check our answers, by the way. Okay, anyway, so we're good. Part E. Suppose that the GCD is this and LCM is this. Find this and this. Is there more than one possibility? Yes. Find all of them. The answer is yes, and it's actually I've actually done it in one of my old videos as well. But this time I'm going to go over this, because this one is a little bit tricky and not as straightforward as the other one. well, it's actually not that tricky. Well, it's tricky, but then it's not as much work as in the other problem. So we see that, well, we're gonna this time we're gonna use we need to use unique prime factorization to help us a little bit. Okay, given that the GCD of m and n is equal to 18. Now we're going to rewrite it as 2 times 3 squared, and the LCM of what is it, m and n is going to be equal to 720, which is same as, what is it, 72 times 10. So 72 is 8 times 9. So that will be 2 to the third power times another 2. So 2 to the fourth power times 3 squared times 5. Okay. So first of all, we of course assume that m and n are positive numbers. Or otherwise, we can make both of them negative, but it doesn't really, it's not really that much interesting if we really talk about it that way. Okay, because again, the negative sign, negative one, is actually a unity. Well, no, it's actually a unit. My bad. Unity is one. Okay, so the negative sign doesn't really help much on understanding the different possibilities. But here's the deal. We know that uh, GCD of m and n is this, implies that both m and n are multiples of 18. So what do we need? So this implies that one of the m n is a multiple of 2 to the fourth power. So multiple to the fourth power, and the other is not a multiple of 2 squared. Okay. Moreover is one single word, my bad. Moreover, one of the mn is a multiple of 5, but not the other one. And both m and n are multiples. Oh, I spelled multiplies. That's why it's kind of weird. Multiples of 3 to the second power because yeah, it is already given there. And then the maximum power is this, but neither of them is a multiple of 3 to the third power. Otherwise, the LCM has to be at least in 3 to the third power. Again, that is the logic behind it. So this is saying that now we have actually a couple options. Well, we have two options, okay? This is now a question of combinatorics. So for the power of 2, we have two options for m. If we choose if we fix the m, then we have only one option of n, and then vice versa. Okay, well, vice versa. So if we choose the n first, then n is fixed. Then later on we choose as a multiple of 5, then we have two options for m, but then but then once we choose m, the n is already is also fixed. So and of course we m and n are playing the same role, so we actually need to see that they're coming in pairs. So actually we end up with uh, uh, by m and n. So with as listed as unordered pairs, we get either m, well, we're gonna pick both m, well, we're gonna pick m to be the smaller versions. So in m is the small version, then we have 2 to the second, well, we have 2 times well, we are not going to take 5 here. Well, sorry, don't forget the 3 square. That's the reason why it's kind of strange. Okay, we don't always have 3 squares on both m and n. Okay, then in this case, if we choose if we fix our m, then n will be forced to be 2 to the fourth power times, of course, 3 squared times, we need to put the 5 there, so we get this, which is, now we have 2 times 9, which is 18. Great. Then for the other one, we have 2 to the fourth power is 16, 16 times 5 at the end, that's 80, times 9, that's 720. So this makes sense, right? Because 18 is definitely an LCM of 720. It's actually, well, 18 times 40 is 720. So we actually have this, it actually satisfies that the GCD is a smaller number, 18. And then the LCM is the bigger number, 720. Good. But we also have the other option that now we still take the small copy of 2. And then don't forget the 3 squared. But now we're going to put the 5 here. Okay. Meaning that now for n, we only have the following. 2 to the fourth power times 3 squared. So in that case, if we multiply them together, we get 90 for the first part. And then the second part, we get 16 times 9, which is 144. Okay, so we see that both of them are multiples of 18. And then divide by 18, we have 5 and 8 respectively. Good. And then we also see that 720 is a LCM. Okay, there's 8 times of 90 and 5 times of 144. So we actually get the two results. Wonderful. So we actually finished problem 4. Now we have like about 50 minutes or less than 50 minutes. Hopefully we can go through one more problem, or maybe not. So it actually looks a lot. Well, let's try to go through the questions itself first. So problem 5 says the 3 plus 1 algorithm works as follow. Start with any number n. If n is even, divide it by 2. If n is odd, replace it with n plus 3n plus 1. Repeat so. For example, if we start with 5, we get the list of numbers 5, 16, 8, 4, 2, 1, 4, 2, 1, 4, 2, 1, and so on and so forth. And if we start with 7, we get 7, jumps into 22, and then gets back down to 11, gets up to 34, 17, 52, 26, 13, and then go back up 40, 20, 10, 5. Then after that, it will just same as the first sequence. Okay. Notice that if we ever get to 1, the list just continues to repeat with 4 2 1s. Okay, so we actually can see it from the first sequence there. Okay, in general, one of the following two possibilities will occur. Okay, one, we may end up repeating some numbers a that appeared earlier in our list, in which case the block of numbers between the two eights will repeat indefinitely. So we actually see an example. If we hit the 1, then it will continue repeating with 4 2 1, 4 2 1 forever. Okay, as a loop. Okay. In this case, we say that the algorithm terminates at the last non-repeated value. So in this case, we will say that 1 will be a non-repeated value. Okay, and the number of distinct entries in the list is called the length of the algorithm. For example, the algorithm terminates at 1 for both 5 and 7. The length of the algorithm for 5 is 6. So what does that mean? Well, if we start with 5, the second number is 16, the number is 8, fourth number is 4, fifth number is 2, sixth number is 1, and we know that it terminates at 1. So then the length will be from 5 to 1 is actually 6 numbers. So we call the length is 6. Similarly, the length of the algorithm for 7 is 17. Okay. Then of course we actually might have a second possible result, which says we may never repeat the same number, in which case we say that the algorithm does not terminate. Okay. So in fact, this algorithm here is actually a very famous conjecture called the Collat's conjecture. Okay, not don't get confused with the Goldbach conjecture. Goldbach conjecture is the conjecture that says for all even numbers greater than or equal to 4, we can always rewrite as a sum of two prime numbers. Okay, or another way of saying it is if we have and for any even numbers strictly greater than or equal to 6, we can rewrite the even number as the sum of two odd prime numbers. Okay, then that one is still not solved yet. And for this one, the Collat's conjecture, known as a 3n plus 1 algorithm, is also not solved yet. Okay, we still haven't had the results that whether we will always get case 1, which we actually see a lot of examples which will terminate at 1, and then we don't know if there's any case 2. Okay, okay, or in other words, we don't know we so far haven't found any counter examples or examples that would not go all the way down to 1, which is actually what the statement of the theory of the conjecture trying to say. Okay, so anyway, we are going to play around with it and trying to solve something very easy, or something that is doable for everyone. Okay, so part A: find the length and terminating value of the 3n plus 1 algorithm for each of the following starting values of n. So first one, n is equal to 21. Second, we have n equals 13. Third one, we have n equals 31. So how does the theorem goes? So we're gonna write down the solution right away. Okay, So we'll just say the algorithm uh, provides us the following sequence. Then I'm going to write like this. So we start off with 21. Since it's odd, we're gonna multiply it by 3, which is 63, and then add 1, we have 64. After that, it's an even number, we're gonna divide by 2, 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 divide by 2. We end up at 1. And in the example, we have already learned that 1 is actually the number that where it terminates, okay? Then we're not going to continue because otherwise we're going to hit back 4 again and then we'll start the loop. Then we'll just terminate there. So uh, so we have the length is, let's see, starting from 21, we have 1, 2, 3, 4, 5, 6, 7, 8. We actually take we actually see eight numbers, okay? So we end up with 8 as a length, and the terminating value is just 1, the last number, okay? Then for part 2, we have we're gonna copy in this thing, and then we're gonna do an adjustment, okay? So this time we start with 31. Okay. Oh, not 31, 13, my bad. 31 is for the next next part. So 31 is odd. We're going to multiply by 3 to get 39 plus 1, that's 40. Then 40 is even, divide by 2, then divide by 2, divide by 2. Aha, we hit 5. And then we know that 5 is not, we know what happened to 5 from the example. But 5 is not the terminating value because, once again, there's not we don't see any loop yet. So if we if we follow the algorithm, we'll get 16, 8, 4, 2, 1. And once again, 1 is at the terminating value because if we start from 1 and continue the algorithm, we'll hit that 4, which is something that actually has repeat or appeared in this in part of the sequence already. So now we know that 1 is the value that we terminate, okay? So second part of the answer is correct. First part, the length is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We see that the length is 10 in this case. So part C, we have we start off with 31 this time. So 31 is odd. So multiplied by 3 is 93, plus 1 is 94. This is even. And then even we're going to divide by 2, get 47, which is odd. So we're going to multiply it by 3 to get 141, and then add 1 more to get 142. Then this is even. We're going to divide by 2, have it, and then we got odd again. We're going to multiply by 3 to get 213 plus 1, 214. Then we're going to have it, 107, and then multiply by 3 to get 321 plus 1, 322. So this one is going to look a little bit long. So we have it, and this is all. We're going to multiply it, and then plus 1, we have 484. Then definitely longer than the last 2 problems, and also a lot longer than the ones in the example. So let's see, we're gonna divide halve it, and then this even, we halve it again to get 121, and then once again multiply by 3, 363 plus 1, 364. So this even, we're gonna have it. This even, we'll still have it, 91. This is odd. multiply by 3 to get 273 plus 1, 274. Okay, and then even, we're going to have it. And this is odd again, we're going to multiply by 3 and then plus 1. If we multiply by 3, we get 400 and what is it? 411 plus 1 is 412. And then we're going to have it to get this. Have it again, we get 103. Then multiply by 3, 309 plus 1, 310. Have it, 165. Multiply by 3. So we see, we kind of see that we actually might get something start off kind of small, but then it actually pops up very long. In this case, 165. So times 3 is going to be 495 plus 1, 496. So this is even. We can finally have it. Try to reduce it, and then this is even again. We can reduce it again, and then we can reduce it again. There is a calculating mistake somewhere. Yeah, there must be there has to be some kind of calculating mistake in my calculations. Let's see. We don't end up with 31, that's for sure. So 31 multiplied by 3, good. 94. Have it, 47 multiplied by 3, that is 141 plus 1, good. Have it, good. Multiplied by 3 is 213 plus 1, good. Have it, good. And then 321 plus 1, good. Have it, this is good. This 1 multiplied by 3 plus 1, this is good. Have it, good. Have it, good. This 1 multiplied by 3 plus 1, good. Have it, good. Have it, good. Multiplied by 3 plus 1, good. Have it, good. This 1 multiplied by 3 plus 1, did I do it correct? 13, let's see, 37, that's 111, 4, okay, good, good, good. This one's good, this one's good. 496, good. Have it, good, have it, good, have it, good. Let's see, I think this is very interesting because we actually found a loop here. Is it? I think there is a I actually made a mistake on my calculations. So, oh, okay, now you see it. So this is what we actually have. Okay. Again, this is what we have for a problem. This is the Kolas conjecture, and then we so far have this. Okay. So we get this. I think there is a mistake somewhere. Okay. I don't think it should terminate as 31, but since it's already time, we'll continue the next time and then see where's the mistake at, and then we're gonna continue finishing this chapter. All right. Okay. So this is it for today. We're gonna end this. We're gonna end this live here. I'll see you guys on the same time on next week.